New analyses of their data are now giving scientists a clearer picture of what actually exists beyond that boundary.
Point down, go ahead. Point at the ground beneath your feet. That direction feels obvious. But someone standing on the opposite side of Earth is pointing the exact opposite way and calling it the same thing. Down doesn't actually exist. Not the way we think it does. And what we've discovered above and below our solar system proves that our mental map of space has been wrong all along. The boundaries aren't where we drew them, and what lies beyond them isn't empty. For decades, astronomy textbooks told a simple story. The solar system is a flat disk. Planets orbit the sun along a thin, orderly plane called the ecliptic. Everything lines up: Mercury, Venus, Earth, Mars, the gas giants, all circling in the same direction, almost perfectly flat. Above and below that plane, mostly nothing. Sparse space, maybe a few rogue comets kicked out by Jupiter's gravity, but nothing substantial. Clean, predictable, organized. The solar system had edges we could define, and beyond those edges was empty interstellar space. That model made sense. Every diagram reinforced it. Planets arranged like grooves on a spinning record. If everything orbits in one plane, then logically above and below should be empty. Except in 2012, something crossed a boundary no human-made object had ever touched. Voyager 1, 11 billion miles from the sun, detected a sudden 40-fold spike in plasma density. The solar wind vanished. Cosmic radiation surged in. It had crossed the heliopause, the edge of the sun's influence. But the boundary wasn't where the models predicted, and its shape didn't match expectations. Not even close. Scientists had assumed the heliosphere, the bubble of solar wind surrounding the solar system, looked like a comet, rounded at the front, stretched into a long tail behind. Physics supported it. Simulations agreed it was tidy and symmetrical. Then in 2020, researchers rebuilt the model using fresh data from Voyager, IBEX, and Cassini. The results shattered the old image. The heliosphere wasn't comet-shaped at all. It was crescent-shaped, like a deflated croissant. The protective bubble surrounding our entire solar system, the shield against galactic cosmic rays, turned out to be warped and asymmetrical, not balanced, not predictable. Twisted and compressed by interstellar magnetic fields we hadn't properly accounted for. The models were incomplete. The pressures were miscalculated. Some interactions weren't even considered. Voyager 1 and Voyager 2 crossed the heliopause at nearly the same distance, 121 and 119 astronomical units, but from different directions. Each encountered different plasma densities and magnetic conditions. The boundary wasn't fixed. It shifted depending on where you crossed it. So when we talk about what lies above or below the solar system, we're already dealing with a boundary that changes shape depending on direction. The edge wasn't where we thought. We were measuring the wrong thing. And that heliosphere isn't even the true outer layer. Beyond it lies something far larger, the Oort cloud. A spherical shell of trillions of icy objects stretching from about 2,000 astronomical units out to perhaps 100,000, halfway to the nearest star. It surrounds the solar system in every direction, above, below, and all around. There's just one problem. We've never seen it. Not a single object, not directly. Every telescope humanity has built, Hubble, Webb, massive ground observatories, can't detect an Oort cloud object unless it falls toward the sun and becomes a comet. And yet, long-period comets keep arriving. Thousands-year orbits, coming from every angle, above the solar system, below it, tilted in directions that defy the flat disk model. Something is out there sending them inward. In 2024, new models added another twist. The Oort cloud might not be a simple spherical shell. It could have structure, regions of higher density, warped zones shaped by the Milky Way's gravitational tides. Over billions of years, the galaxy's gravity may have pulled and distorted the cloud, sculpting it into complex forms. Those same tidal forces occasionally dislodge objects, sending them spiraling toward the inner solar system as long-period comets. So the structure surrounding us, the true outer boundary of the solar system, isn't defined by the sun alone. It's shaped by the entire galaxy. The Milky Way is actively sculpting the solar system's edge, which means the solar system isn't isolated. It's embedded in something much larger. And then comes the final twist. The ecliptic plane, the flat surface where all the planets orbit, is tilted about 60 degrees relative to the Milky Way's galactic plane dot. That means when we look up from Earth, we're not looking out of the galaxy, we're looking through it. Straight up from the solar system's north pole doesn't lead to empty space. It cuts into the densest regions of the Milky Way. Billions of stars, nebulae, and molecular clouds. Constellations like Draco hang overhead. Polaris sits near the north celestial pole, but they aren't special because they're above us. They're just in that direction because of how our solar system formed. 4.5 billion years ago, a collapsing cloud of gas and dust spun into a disk. Its orientation was random. If it had rotated differently, up would point toward entirely different stars, different constellations, different parts of the galaxy. Direction in space has no universal meaning. It's a local concept. On Earth, gravity gives us a reference, up and down. In space, there's no such thing. Every solar system has its own orientation. Every galaxy has its own plane. Every cluster aligns differently. We thought mapping above and below our solar system meant charting empty space. Instead, we discovered layers. First, the heliosphere, warped, asymmetric, shaped by interstellar magnetic fields. Then the Oort cloud, spherical, invisible, influenced by galactic tides. Beyond that, interstellar space, filled with hydrogen clouds, cosmic rays, and magnetic fields. Then the Milky Way's disk, tilted 60 degrees relative to our planetary plane. Farther out, the local bubble, the local group, the supergalactic plane. Each layer redefines what above and below even mean. Voyager 1, the farthest human-made object ever launched, won't reach the inner edge of the Oort cloud for another 300 years. It will take about 30,000 years to cross it completely. 30,000 years moving through a region we can't see, filled with objects we've never directly observed, shaped by forces we're only beginning to understand. And during that entire journey, Voyager will still technically be inside the solar system, because the solar system doesn't end where the planets stop. It doesn't end at the heliopause. It ends at the outer edge of the Oort cloud, where the sun's gravity finally loses its grip to the Milky Way. That boundary sits somewhere between 100,000 and 200,000 astronomical units, roughly 1 to 3 light years from the sun. And we have no way to observe it directly. No spacecraft will reach it in our lifetimes. No telescope can image it. The edge of our solar system is effectively invisible. And beyond that edge, other solar systems, other Oort clouds, possibly overlapping with ours. Interstellar clouds of gas and dust. The galaxy's magnetic field threading through everything. We don't live inside a neat, isolated bubble. We exist inside overlapping spheres of influence, nested structures with boundaries that shift and blur into each other. There is no clean edge. There is no empty space above or below. There are only more layers, more forces, more structures waiting to be understood. So what lies above and below our solar system? The answer keeps changing. Every time we define the boundary, we discover another layer beyond it. Every time we assume a direction is empty, we find it filled with something unexpected. The heliosphere isn't shaped the way we thought. The Oort cloud surrounds us invisibly. The galaxy itself is pulling on the solar system's edges. And the directions we use to organize reality, above and below, don't actually exist once you leave Earth. We thought the question was simple. We thought the answer was nothing. Instead, we found that the solar system has no sharp edges. It has gradients, regions where one influence fades into another. The directions we use to describe them are as arbitrary as the spin of a gas cloud billions of years ago. The solar system isn't a flat disk floating in empty space. It's a nested structure, embedded in a galaxy, shaped by forces operating on scales so vast we can barely measure them. So what's above and below us? Everything we didn't expect.